Let's suppose that you live in a one-dimensional world. It's a very simplistic example, but if you read Flatlandia, you are very familiar with this example. We want neurons in our brain to encode the information about the position in this world, which is simply a line. Neurons communicate by varying the number of spikes emitted. One possible way to encode our position in this space is to have neurons which are active in different regions of the space. So, for example, we may have the red neurons which is active here, the green neuron which is active here, and the blue neuron which is active here. Now, if my red neuron is active, I know that I will be here. If my green neuron is active, I know that I will be here, and if my blue neuron is active, I know that I will be here. This is exactly what is found in mice, which possess these kind of neurons which are tuned to the position of the animal in the space. But actually, there are neurons which present much more complex tuning profiles, and this was exactly the object of study of my PhD. So, for example, these neurons may have random tuning profiles and always being active across all the positions in the space. So we may have a blue neuron which is active in this way, a green neuron which is active in this way, and a red neuron which is active in a different way. You may say that this is a very stupid way of encoding the position, because if I know that my blue neuron is firing this number of spikes, I know that I can be here, I can be here, I can be here, and I can be here. And if I'm actually here, saying that I'm here will cause a very large error in my stimulus, in my position estimate. But instead, if I'm able to collect information for all these three neurons, and I know that the red neuron spikes here and green neurons is active here, I can show that there is only one position, which is this position, which corresponds to exactly this pattern of firing of these three neurons. Another interesting property of this system is that if I increase the dimension of my world, in this way, in this population of neurons, I will add a number of neurons which is proportional to the size of the space which is added. Instead, here, these neurons will be also active in the added amount of space, and I will have to add a very few number of neurons to make sure that also the positions here are represented by just one activity pattern of these three neurons. In practice, if the size of my world is L, and I call the error in my stimulus estimate epsilon, while in the first case I will have that the ratio between the size and the error scales linearly with the number of neurons, in the second case with random tuning curves, this ratio scales exponentially with the number of neurons. So with few neurons, I will be able to encode my information much more precisely. You may think that this is a very abstract way of encoding information, but actually, in monkey motor cortex, neurons are selective to the position of the end of the monkey exactly in the same way. You just need to extend the theory to higher dimensional spaces, but this is a thing that we managed to do. So, one problem of these coding schemes is that it might be very hard to decode. These neurons will send signal to all the brain, so the brain machinery will have to perform the inverse operation and map back the activity of the neurons to the position in this world. In this case, the brain machinery will be very simple because it just has to keep into account the color of the neurons to obtain a very good estimate of the position. Instead, in this case, the brain machinery will be much more complex because it will have to keep into account all the pattern of activity of the neurons to decode the position in the space. what we did is to study how the properties of the encoder will depend on the features of the encoder, so how complex these tuning curves are, but also how powerful this brain machinery is. So, to conclude, we saw that random complex neural responses are a very powerful encoding tool to encode a lot of information with few number of neurons. But we also saw that the optimal degree of complexity will depend on the decoding machine. Too simple decoding machine will not be able to take advantage of the complexity of the encoder.
I don't know. So what do you want to say?
It was very nice experience, and this video was harder than all the 3 years of vacation.